to the parameter estimation. The first speaker, and again, I'm sorry if I mispronounce your name, is Soichiro Morisaki, who is a LIGO member of the University of Tokyo, and is working on parameter estimation for compact binary searches and also dark matter searches. And I leave you the floor, but okay, now I see the slides. So go on, and sorry, before you start, as usual, put your question in the channel, in the topic of Ask Igwin about the lecture number 3. I sent you the link yesterday, you should have it.
Hi, can you hear me? Sorry. Okay. Thank you for the introduction. And hi, everyone. Thank you for coming, joining the workshop today. Today, I'm going to, so I'm Soichiro Morisaki, working at the University of Tokyo. Today, I'm going to talk about the inference of the source parameters of compact binary crescent signal. So yesterday, we had a nice overview. Sorry, I have, okay, yep. Okay, so yesterday we had a nice overview from about the compact binary crescent search from the COSTA. And after the search finds signal, then the next important task is to interpret the signal and extract physical or astrophysical information from the signal. So in this talk, I'm going to talk about what information we can get from signal and how to do it. So this slide basically summarizes the problem we are considering here. From the observed signal, what we want to do is to infer the properties of the source, such as the masses of the colliding objects. So the right figure shows the probability distribution of the masses of colliding objects of GW 150914, which is the firstly discovered gravitational wave signal. So the horizontal axis shows the mass of the heavy object, which is denoted by M1. And the vertical axis shows the mass of the light object, which is denoted by M2. So the M1 is by definition larger than M2. So we only need to consider the lower light region in this panel. And here, this color intensity represents the probability value. And this contour encloses the region whose total probability is 90%. So basically, roughly speaking, this region, the true values of the masses are likely to be located at this region. So, and our goal here is to obtain this kind of probability distribution for all the parameters we can measure from gravitational wave data. So at the first of the talk, let me introduce what parameters we can measure from gravitational wave data. So first of all, as I introduced in the previous slide, we can measure the masses of colliding objects. So the right figure shows the signal starting from the 20 Hertz with different masses. So this symbol here, M dot, represents the mass of the sun. So the blue one signal is from the 35 solar mass, 25 solar mass binary, while the orange one comes from the 25 solar mass, 15 solar mass binary. And as you can see in this figure, because the heavier binary emits higher energy with gravitational waves, the signal from the heavier binary more quickly evolves toward the merger, and the signal gets shorter and has a higher amplitude. So observing this, how rapidly this signal frequency evolves, we can measure the masses of colliding objects. Doing some calculation, we can also show that the frequency evolution of the signal is predominantly determined by this mass combination, which is called the Chern mass. So in a typical analysis, for typical signal, we can measure this Chern mass combination most precisely. In addition to the masses of the colliding objects, the spin angular momenta of the colliding objects also affect the frequency evolution of the signal through the general relativistic effect. So, and we can show from the general relativity that the most what predominantly determines the frequency evolution are the spin components in parallel with the orbital angular momentum. So that this movie, this movie shows the binary evolution with 3 different spin configurations. The left figure is for in the left figure, spin angular momentum are aligned with orbital angular momentum. In the middle, spins are vanishing. In the right, the spins are completely anti-aligned with orbital angular momentum. And what we find in this movie is that the aligned spins slows down the binary evolution, while the anti-aligned spins accelerates the binary evolution. So you can see that the right binary is the first to merge, and then the next is the middle one to merge, and then final one is finally the left one is merged. So observing how rapidly this signal frequency evolves, we can also measure the spin components in parallel with the orbital angular momentum. In addition to the parallel spin components, we can also measure the spin components orthogonal to the orbital angular momentum, observing the amplitude and phase modulation of the signal. So the reason why is if the spins are not misaligned with the orbital angular momentum, then that misaligned components causes the orbital plane to precess, and you see the you see that the orbital angular momentum slowly changing its direction with time, and reflecting this slow modulation. You can see in the bottom figure that the amplitude and the phase of the signal slowly modulates. So observing this amplitude and phase modulation, you can also measure the orthogonal spin components. And using those observations, we can measure masses and some components of the spins. And those are the key information to prove the formation history of merging binaries, because they reflect how binaries are formed in the universe. Okay, and in addition to masses and the spins, if the binary contains a neutron star, then the neutron star is tidally deformed by the companion star like this, so tidally deformed. And this tidal deformation also affects the frequency evolution of the signal. So this right figure shows the signal with and without this tidal effect. So as you can see in this figure, this tidal deformation accelerates the rate in spiral motion of the binary and makes the signals slightly shorter. Okay? And this tidal effect, the significance of this tidal effect is actually dependent on the so-called tidal deformability parameter lambda. So observing this tidal effect, you can measure the tidal deformability parameter lambda of this neutron star. Since this tidal deformability parameter depends on the properties of the highly dense matter composing the neutron star, using this observation, you can also constrain the properties of the highly dense matter, which has not been fully understood by the previous experiments. In addition to those parameters, it is also important to measure the direction source rotation, and it is especially important for the follow-up electromagnetic observations, follow-up electromagnetic observers. And we can measure that the direction to the source using the data from multiple detectors. So the idea is, if we have multiple detectors at those locations, and suppose that gravitational waves are coming from this direction, then this gravitational waves first hits this detector, then next this detector, and then hit this detector. So we see arrival time differences dependent on the source direction, and using this information, you can constrain the source. Direction. We can also use the signal amplitude at multiple detectors, because the sensitivity of the detector is also dependent on the source direction. So using the different observed signal amplitude at multiple detectors, we can also constrain the source direction. And combining those information, we can obtain the this kind of two-dimensional probability distribution of the source rotation. And this information is especially crucial for the follow-up observers to determine where they point their telescopes. Okay, so to summarize, this is a standard list of the parameters characterizing the gravitational compact binary crescent signal. So we have, as I explained, we have masses, spins, tidal deformabilities, and source rotation parameterized by light ascension and declination. In addition to those parameters, we have also coalescence time, distance to the source, and some angle parameters characterizing the geometrical configuration. So in total, we have 15 parameters for binary black hole and 1 additional tidal parameter per neutron star. So there we have a lot of parameters. And I would also like to note that in the actual analysis, we use different parameterizations for masses, spins, and light ascension declination and coalescence time to improve the computational efficiency, but it is kind of a bit technical data. Okay, so they are the parameters we can measure from gravitational wave data. And next, I will talk about how to infer them. So as I said, the information of the parameters are imprinted on the gravitational wave signal, plotted in red in this panel. However, as we learned from previous talks, the gravitational wave signal is typically tiny, and it is typically buried under the instrumental noise, which is plotted in blue in this panel. So to infer the parameters taking into account the noise uncertainties properly, we start from the data model that data is modeled as the sum of the CBC signal, denoted by H, and parameterized by the parameters theta and noise, which is denoted by N. Here, this parameters theta should be regarded as the vector of all the parameters characterizing the CBC signal. Okay, and for noise, we make the following two assumptions. One is that we assume that instrumental noise is stationary process. So basically, we assume that the statistical properties of the noise do not change with time. And to be more concrete, we assume that the expectation value of the noise is constant with time, and the two-point correlation of the noise only depends on the difference time difference. And under these assumptions, it can be shown that the Fourier components of the noise actually have a nice properties. So to be more concrete, if you calculate the expectation value of the Fourier component of noise, then it is vanishing for the non-zero frequency component. So here, this FL represents the L's frequency beam, and this large T represents the data duration. And more important thing is that if you calculate the correlation of the different frequency components, then you can, under these assumptions, you can show that they are vanishing. And this correlation is proportional to the Kronecker delta symbol. So you can simplify this correlation matrix using the Fourier transform. And here, this S is defined by the noise variance normalized by the observation time. And this S is referred to as the power spectral density, or PSD for short. And this quantity is useful to characterize the noise significance at that frequency. And the second assumption is that basically we assume that the noise follows the simple Gaussian distribution. And combining those two assumptions, we can show that the noise, each frequency component of noise follows the statistically independent Gaussian distribution like this. And this distribution is referred to as Whittle likelihood. And using this Whittle likelihood model, we can easily calculate our likelihood, which is the probability of obtaining data, assuming true parameter values theta. So basically, we can start from this with likelihood of the noise, and remembering that the data is the sum of the waveform H and noise N. We can reduce this N to the data minus waveform, and we obtain this likelihood form, this likelihood functional form. And observing this likelihood, you can immediately see that if the likelihood gets higher when this residual at the numerator gets smaller. So you can see that this likelihood basically quantifies how well the template waveform fits data. And so far, we only consider single data from a single detector. But we can easily generalize this likelihood functional form to the multiple detectors. So assuming that the instrumental noise from multiple detectors are statistically independent, we can show that the likelihood from multiple detector is just a product of the product of likelihood at each detector. So we obtain this form. And to compute this likelihood, of course, we need to calculate the power PSDS. And as you can see, because the PSD is basically the noise, the expectation value of the square of the noise, the straightforward way to estimate this is to take a lot of data sets feature away from the signal and just calculate their average. So the PSD estimated in this way using the data on the GW500914 is shown in this in the right figure. However, there is a drawback of this method so this method basically assumes that the noise spectra do not change over the data sets we are using for PSD estimation. And it could be biased if the noise spectra change with time. So to mitigate the biases caused by that kind of noise non-stationarity, there is another PSD estimation algorithm called the baseline algorithm, which basically fits the spectra of on-source data using some assumed functional form. And if you are interested in this baseline algorithm, you can refer to the Littenberg and the Cornish paper linked here. Okay, so now we can compute the likelihood of of gravitational wave data. And on the other hand, as I said at the start of this presentation, what we really want to calculate is the probability of obtaining probability of parameter data. Because so on the other hand, the likelihood is the probability of obtaining data conditioned on theta. So we want to flip data and theta parameter theta here, and we use Bayes theorem for that. So what Bayes theorem tells us is that you can calculate the probability of obtaining parameter theta conditioned on theta by multiplying likelihood by the probability of obtaining parameter theta, and normalize it by the probability of obtaining data. And in this Bayesian inference framework, we call the probability of probability distribution in the left-hand side posterior probability distribution, and this probability of obtaining theta is called the prior probability distribution. And this normalized factor is called evidence. Okay, and I will before moving to the next slide, I will slightly change the notation here to make this consistent with the notation in the tutorial notebooks. So from now, I'm going to use L for the likelihood, pi for prior distribution, and Z for the evidence. I'm also now writing explicitly write that those probability distribution are conditioned on the our hypothesis or model. For example, this hypothesis or model M can be regarded as the choice of the waveform model we use for the for calculating the template waveform H tilde. For example, we may want to use very simple waveform model based on the post-Newton approximation, or we may want to use a more accurate waveform based on the numerical relative distribution. And this kind of choice can be expressed by this hypothesis or model M. Okay. Now, to compute this Bayesian posterior distribution using this formula, we also need to specify this prior probability distribution. And in the typical gravitational wave inference, we typically determine this prior distribution based on our prior knowledge or belief on the parameters data. For example, if we don't have any information about the parameters data, then we can use the completely uninformative prior on them. For example, if we don't have any information about the source direction, then we can use the isotropic distribution on light ascension and degradation. Or if we don't have any information about the masses, we can use a uniform in mass prior. On the other hand, if we have some information about the parameters, then we can easily incorporate that information in the prior. For example, if we know the source rotation from the electromagnetic observations, then we can use the delta function like prior centered on that rotation. While if we know the mass distribution from previous observations, then we can use that distribution as prior. On the other hand, this evidence is just a normalization factor of the probability distribution, and we don't need to compute it for inferring the source parameters. However, on the other hand, if we want to compare, if we have two different hypotheses or models we want to compare, then this evidence value is useful. For example, if we have two different hypotheses M1 and M2, then we compute the evidence values for two models and compare their values. And if we find that the evidence value is higher for model M1, then we can claim that M1 is favored by data and vice versa. Okay. So this is the basics of the posterior Bayesian inference. And now we know how to compute posterior distribution. However, unfortunately, it is still hard to extract astrophysical information from that because the posterior probability distribution is the function of many parameters. So as I explained in the previous slide, we at least have 15 parameters, and to extract the useful information on astrophysics, we need to reduce the distribution of that high dimension to the distribution of a few selected parameters we are interested in. So for example, if you are interested in secondary mass M2, then we need to integrate this distribution over the parameters except for M2 to calculate the one-dimensional probability distribution like this. And or if we want to know the source direction, then we need to integrate this over the parameters except for light ascension degradation to calculate the two-dimensional posterior distribution. And obviously, as you can see, that they require high-dimensional numerical integration, which is practically very difficult to do. But fortunately, we have a path forward here, and we can use the stochastic sampling algorithm to solve this problem. So the idea is, so rather than doing this high-dimensional numerical integration, we can generate the random samples following this posterior probability distribution and make their histogram. So for example, if you are interested in the secondary mass M2, and if we have random samples following the posterior distribution, then we can read the M2 value from each sample and make the histogram of them like this to obtain the one-dimensional histogram. And in that way, we can easily make a distribution of whatever parameters we are interested in. This stochastic sampling method still requires the method to efficiently produce the posterior samples. But again, fortunately, we have several efficient algorithms for doing that. For example, the Markov chain Monte Carlo method or MCMC method is an efficient method for producing posterior samples and popular and widely used in various approximations. In addition to that, in gravitational wave application, we also often use the nested sampling algorithm, which is known to be a robust algorithm for even if the posterior has a complex structure. Okay. And to give you a rough idea on how these sampling algorithms work, I will also introduce one of the simplest MC algorithms named Metropolis Hastings algorithms. So I will illustrate how this algorithm works with this two-dimensional simple Gaussian distribution. So here, those lines represent the counter lines of the distribution, and here is the peak of the Gaussian distribution. So this algorithm first starts from the randomly selected point, which is shown here. Then using the user-specified proposal distribution denoted by Q, it proposes a next point theta prime, which is denoted by theta prime randomly. Then and this algorithm randomly accepts that proposal using with this probability shown here. And if this proposal is accepted, then this it jumps to this next point proposed by this proposal distribution. You can looking at this probability, the form of probability. You can see that this probability is proportional to the ratio of the probability of the next point and the probability of the current point. So the jump to the point which has a higher probability is more likely to accept it. So repeating this procedure, the point is rapidly moves toward the center of the distribution. So the light movie shows the thousands of points repeating this procedure, this acceptance and proposal and acceptance procedure. And interesting thing is that mathematics proves that the point repeating this procedure automatically converges to the sample following the posterior distribution. So due to this fact, so after enough number of iterations, these iterations, we can use those random points as the samples following posterior probability distribution. Okay, and I would also like to note that this is again the simplest algorithm of the stochastic sampling, and we have there have been various more efficient algorithms developed in the last decades. To do this, we need a cause for that. But fortunately, we do not need to implement this algorithm from the scratch because there are various nice open source samplers. For example, for MCMC, we have EMCE codes, PTEMC library, and there are other libraries. For nested also for nested samplers, we have a dynasty library, which has been frequently used for the LIGO-BAGO-KAGR analysis and other nested samplers. So if you have a distribution you want to you want to draw samples from, then you just need to install one of them and use it. Another good news is that you don't even need to implement gravitational wave likelihood prior from the scratch because we have a open source user-friendly library named BULB for that. So this BULB has been extensively used for the previous LIGO-BAGO-KAGR analysis. This library is written in Python, so it can be easily installed with pip and conda. And the BULB already has all the necessary components for CBC parameter inference built in. For example, this library has a gravitational wave likelihood, frequently used priors, and useful parameter conversion functions. It also supports the open source samplers I presented in the previous slide, and it also has a native sampler named the BULB MCMC, so you can use whichever sampler you want to use in your inference. BULB is also not restricted to the CBC problem, and it can be used for analyzing the gravitational wave signal with general morphology, or it can also be used for simulating CBC signals as well as analyzing real data. And you will learn how to use this library using the tutorial notebooks we have prepared. Okay, so that's basically all for the basics of the gravitational wave inference. And I will very briefly, finally, I will very briefly introduce how to deal with the posterior samples produced by this produced in the gravitational wave inference. So if you want to work with the posterior samples for posterior samples for the real signals we detected in the previous observing runs, you can download the posterior sample files from these links. And if you read these sample files, then you will find that the sample file actually contains this kind of spreadsheet where each column contains the samples for each parameter. And if you want to, for example, if you want to get the one-dimensional posterior distribution of one of the parameters, then you can just read one of the columns, and then you can just easily make the histogram using the Python code, using simple Python code. Or if you want to know the 90% credible interval, then you can easily calculate the fifth and 95th percentiles of the samples and draw the vertical lines there. Or using the popular Python module called Corner, you can also make the two-dimensional histogram of the samples, and it is especially useful for to understand the correlation of the multiple parameters. And you will learn more about reading and plotting the samples with the tutorial we have prepared. Okay, so basically that's it. So the conclusion, we can measure source parameters such as masses, spins, and tidal deformalities using gravitational wave data. And so this inference is typically performed with Bayesian inference framework, where likelihood is computed under the assumption of stationary Gaussian noise. And to tackle the high-dimensional problem, we generate random sample following this Bayesian probability distribution and make their histogram to estimate the source parameter values. And if you are interested in more details about it, you can refer to the BLB document linked here, or nice review article written by Srein and Taro. So basically that's it. So thank you.
Thanks a lot, Soichiro. How is the correct pronunciation?
Yeah.
Soichiro. Oh, thanks a lot for this comprehensive lecture. I will read some of the question in the chat on ask.equin, but before I want to say one thing that is a question for you, but a general comment. So in this tutorial, when we ask the students to run some of the analysis, usually this analysis take few minutes. In some exercise we ask to modify something, and in some case takes 10-20 minutes if you run on Colab. But how long it takes normally in the real case, the analysis to get the parameter estimation for one real event in our analysis? Rough estimate.
Yeah, so that's a good question. So it really depends on the signal duration. For binary black hole, which has a short duration, then the analysis is computationally cheap, and it typically takes hours or at the longest day. But for the binary neutron size signal, which has a longer duration, then the analysis is more costly, and it can take months or even years. But so to solve this problem, there have been various techniques developed. For example, the techniques named the reduced order curvature, and using such kind of approximate methods, you can reduce the analysis time to hours or day for the binary neutron size signal. Yeah.
Okay, so just to, I asked just to stress that the exercise has a simplified version, but in the real case, it takes longer and it's not, so some student ask me, but don't we have a place where to run this to make it faster? No, because in our, it's also a problem for the collaboration because it's a very complex method. Okay. So the last question that I see in the chat is, can you explain Bayesian inference in layman's terms?
Actually, I don't understand the question. What, layman's theorem? Sorry.
It means in easy words, in very easy words.
Sorry, what you said? Layman's theorem?
Yeah, it means in a very easy way, in very easy words for people that are non-expert.
So I think it's just explain it again in a simpler way.
Of the Bayesian inference?
Yes.
Basically, you mean the explanation of the Bayes theorem? Then, sorry if I don't know. I understand your question, but basically, so if you need an explanation of the Bayes theorem, then it's basically, the probability of probability of obtaining theta conditioned on data multiplied by the probability of obtaining data is basically the probability of obtaining theta, obtaining parameter theta and data. And you can also compute that probability in a different way. So we can compute that probability by multiplying the probability of obtaining data conditioned on theta and multiply it by the probability of obtaining theta, and using that equality and make move this probability of obtaining data to the denominator of the right hand side, then you can obtain this equality. Sorry, I don't know whether I understand your question, but.
Yeah, and I don't know, I'm reading what's written here. If the student that have asked, you can discuss in the chat after. And the same student asked if parameter estimation and noise reduction are related.
So typically, in the standard, it could be, for example, we could do a simultaneous inference of the gravitational wave signal and some noise model to reduce the noise effects. But what we typically do in the LIGO-Virgo-Kaggle analysis is that before doing the parameter estimation, we work with the detector experts to first mitigate the noise in the data and then start the parameter estimation. So the noise reduction is completely a separate process from the parameter estimation.
Okay, so I think, okay, there is another question that was asked in different points, position. So how to generate the movie of that was shown earlier about the CPC. I think it was already someone replied on ask.iguin, but
Yeah, so this is actually nice. This is from the nice work by the BJ on the. So you can just search for the binary black hole explorer, then you will have access to the bunch of the nice this kind of movies, and I think the cause to produce this movie. I'm not sure, but yeah, just Google this binary black hole explorer.
Okay, so I think we have more or less finished all the talking. So in the meanwhile, someone is asking if the meeting are recorded. Yes, So if you go in the GWOSC page, every day after we finish the lecture, I send an email to all the people registered. So if you have not received, it means that either you have not registered or you have not checked your email. So I've sent in these days, every day, a link to the recorded lecture every day. And also I put the link on the GWOSC page from which you register to this meeting. So, and also it has been added to the Thinkific. So it's in so many different places that you cannot miss the registration, the recordings. Okay. So I think we should close this talk now and go to the next speaker. Thank again Soichiro, and if there are remaining questions about this talk, continue on ask.iguini.org, and I may ask the speaker to